Hello, welcome back to Discrete Calculus with the Wolfram Language. I'm Alistair Forsyth, and this video will be all about generating functions. So a generating function is an infinite power series whose coefficients are the elements of a corresponding sequence. For example, when given the sequence a sub 0, a sub 1, a sub 2, and so on and so forth up to a sub n, we could write the generating series big A of x, which would then be equal to a sub 0 plus a sub 1 x plus a sub 2 x squared, and so on and so forth. Overall, big A of x will be equivalent to the infinite sum starting at n equals 0 of a sub n times x to the power of n. When working with a generating function, the variable x in big A of x is called the auxiliary variable. Sometimes people say big A of x enumerates the sequence a sub n. Along with that, when working with generating functions, people often use the notation of x to the power of n in brackets, big A of x, as the coefficient of x to the power of n in big A of x. Now, there are actually a handful of different types of generating functions, but in this lesson, we'll focus on ordinary generating functions. Now, I want to take a moment here to address that many of the examples used in this lesson, and many of our other lessons, come from Concrete Mathematics by Ronald Graham, Donald Knuth, and Orrin Potashnik. I would say Concrete Mathematics is easily the best textbook I have ever read, and I would heavily recommend checking out a copy if you enjoy this course. It's definitely not an easy read, but it's certainly worth the time you put into it. Now, before we look at the main properties of generating functions, there's actually two different applications we can see right off the bat. Firstly, the binomial theorem shows us a generating function for the binomial coefficient of n, k in terms of k. To put it fresh in our minds, the binomial theorem shows x plus y to the power of n will equal the sum from k equals 0 to k equals n of the binomial coefficient of n, k times x to the power of n minus k times y to the power of k. According to the binomial theorem, 1 plus x to the power of n is equal to the sum from k equals 0 to k equals n of the binomial coefficient of n, k times x to the power of k, making 1 plus x to the power of n a generating function for the binomial coefficient of n, k. Similarly, a generating function for the binomial coefficient of n, k in terms of n can be found as x to the power of n divided by 1 minus x to the power of n plus 1, which is then equal to the sum from k equals 0 to k equals n of the binomial coefficient of k, n times x to the power of k. Along with that, we can use generating functions to demonstrate an application of the Fibonacci numbers that we covered in a previous video. The question was, how many different ways can you cover a 2 by n rectangle with 2 by 1 dominoes? To answer this, we'll start by examining the base cases. When n equals 1, our number of ways will also be 1, as you can only cover a 2 by 1 rectangle in one way with 2 by 1 dominoes. When n equals 2, t will also equal 2, as you can either cover the space with horizontally placed dominoes or vertically placed dominoes. Building off of that, when n equals 3, t will also equal 3, as you can add a vertically placed domino to either configuration of n equals 2. To clarify why this is 3, there are two ways to add a vertically placed domino to the horizontally placed configuration of n equals 2, whereas there's only one way to add a vertically placed domino to a vertically placed configuration of n equals 2. Now, this seems like it's starting to build a recurrence relation of t sub n is equal to t sub n minus 1 plus 1. However, this is broken when you consider that when n equals 4, t equals 5, as you can either have two variations of n equals 2 together or add a vertical domino to n equals 3. Now, if any of these base cases are confusing to you, try writing out every configuration for n equals 1, 2, 3, and 4 by hand on a piece of paper with a pencil, as there was only 11 configurations, and it'll make understanding the rest of this proof much easier. From here, we can notice the pattern that t sub n is then equal to t sub n minus 1 plus t sub n minus 2. Running through this, we can verify that t sub 3 is equal to 1 plus 2, which is 3, and t sub 4 is equal to 3 plus 2, which is 5. Now, to justify this as n grows without bounds, we can see that the left term of t sub n can be two horizontal dominoes added to a variation of t sub n minus 2, or the left term of t sub n could also be a vertical domino added to a variation of t sub n minus 1. This means that we can create a new variation of t sub n from any variation of t sub n minus 1, or from any variation of t sub n minus 2, which then gives us the formula t sub n is equal to t sub n minus 1 plus t sub n minus 2. From there, we can write out a summation of all possible values of n. We'll use v to represent a vertically placed block, and h to represent a horizontally placed block. Brackets will indicate a full 2x2 area that's covered. To add to that, we'll consider t sub 0 equal to 1, as there's only one way to fill a non-existent space. From here, we can write out t is equal to nothing plus 1 vertical block plus 2 vertical blocks plus 2 horizontal blocks plus 1 vertical block and 2 vertical blocks plus 1 horizontal block and 2 vertical blocks, and so on and so forth. From there, we can factor out a vertical block and 2 horizontal blocks to get t is equal to nothing plus a vertical block times nothing plus a vertical block plus 2 vertical blocks, and so on and so forth, plus 2 horizontal blocks times nothing plus a vertical block plus 2 vertical blocks, and so on and so forth. From there, we can rewrite this as t is equal to nothing plus a vertical block times t plus 2 horizontal blocks times t. Finally, we can move some pieces around to retrieve a generating function for t sub n. First, we subtract the vertical block times t and the 2 horizontal blocks times t from both sides, giving us t times nothing minus a vertical block minus 2 horizontal blocks is equal to nothing. Then we can divide by nothing minus a vertical block minus 2 horizontal blocks to get 1 over 1 minus a vertical block minus 2 horizontal blocks. Then, leaving our silly little block notation, we can convert that into t is equal to 1 over 1 minus x squared. And now for the big reveal. If we take series of 1 over 1 minus x squared, as x goes from 0 to 10, we get a power series with the coefficients of the Fibonacci sequence. Now, if you're a bit of a stickler for proofs, you might not be satisfied with just seeing 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and 89 in a row and calling that the Fibonacci sequence. However, we know that this must be the Fibonacci sequence because it follows the recurrence relation t is equal to t sub n minus 1 plus t sub n minus 2, and its starting values of t sub 0 and t sub 1 are both 1. Because it possesses that recurrence relation, we know that it must be a linear combination of the Fibonacci sequence and the Lucas series. However, when you take that linear combination, the Fibonacci's coefficient will just be 1, as it's 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on and so forth. Altogether, before we've looked at any properties of generating functions or any real manipulations of them, we can already see 3 different generating functions, which I think is pretty cool. Now, going back, we can look at some simple properties of generating functions. To start with, multiplying a generating function by a coefficient, let's say alpha times f of x plus beta times g of x, we'll just take that coefficient and separate it out of the sum. This means that for arbitrary generating functions, alpha times big F of x plus beta times big G of x will be equal to alpha times the infinite sum starting at n equals 0 of f sub n times x to the power of n plus beta times the infinite sum from n equals 0 of g sub n times x to the power of n. Now, if it's contextually helpful, we can then simplify that further to alpha times big F of x plus beta times big G of x is equal to the infinite sum from n equals 0 of alpha times f sub n plus beta times g sub n multiplied by x to the power of n. Now if we take a generating function of a coefficient times its auxiliary variable, let's say big F of cx, that'll be equal to the infinite sum starting at n equals 0 of f sub n times cx to the power of n, which will then be equal to the infinite sum starting at n equals 0 of f sub n times c to the power of n times x to the power of n. Effectively, this means we can think of big F of cx as either the generating function for f sub n, c sub n, or the generating function of f sub n with an auxiliary variable of cx. Now differentiating a generating function, big F prime of x, will give us the infinite sum starting at n equals 0 of n plus 1 times f sub n plus 1 times x to the power of n. Using that, we can retrieve x times big F prime of x is equal to the infinite sum starting at n equals 0 of n times f sub n times x to the power of n. Along with that, we can retrieve the integral from 0 to x of big F of t dt will be equal to the infinite sum from n equals 0 of 1 over n times f sub n minus 1 times x to the power of n. Finally, we can see that when we offset our auxiliary variable, say taking x to the power of m times big F of x, we can either retrieve the infinite sum from n equals 0 of f sub n times x to the power of n plus m, or we can retrieve the infinite sum starting at n equals 0 of f sub n minus m times x to the power of n. Now, if some of these manipulations involving infinite sums are confusing to you, that's completely fine, because we actually have 2 videos coming out soon on finite sums and infinite sums, respectively. Moving on, generating functions have a special type of product, called a convolution. Now, if we multiplied big F of x times big G of x, we would get f sub 0 plus f sub 1 x plus f sub 2 x squared, and so on and so forth, all multiplied by g sub 0 plus g sub 1 x plus g sub 2 x squared, and so on and so forth. This would then leave us with f sub 0 times g sub 0 plus f sub 0 times g sub 1 plus f sub 1 times g sub 0 times f plus f sub 0 times g sub 2 plus f sub 1 times g sub 1 plus f sub 2 times g sub 0, all multiplied by x squared, and so on and so forth. Finally, we can rewrite that as the infinite sum from n equals 0 of the infinite sum from k equals 0 of f sub k times g sub n minus k, all multiplied by x to the power of n. Now this is typically called the convolution of big F and big G of x, but sometimes it's also called the Cauchy product. Now something that's important to observe here is that the coefficient of x to the power of n in big F of x times big G of x will be equal to the infinite sum from k equals 0 to k equals n of f sub k times g sub n minus k. To help us handle all of this, we have some helpful functions in the Wolfram language that are related to generating series, which include generating function of series, n, x, which returns a generating function for the series using the auxiliary variable x, where n is the index for the series. Along with that, we have series of a function and x sub 0, and n, which returns a power series of degree n centered at x sub 0, which estimates the function. Finally, we have series coefficient of series, n, or series coefficient of function, x sub 0, n, which returns the coefficient of the nth element in the series. Finally, we have series coefficient of series, n, or series coefficient of a function, x sub 0, and n, which returns the coefficient of the nth element in the series. Now, some notable examples of ordinary generating functions include the generating function for f is equal to 1, which will be 1 over 1 minus x. We can confirm this by entering f of x is equal to 1 into generating function of f of x, comma x, comma x. Next, we have 1 over 1 minus x squared, which generates 1, 2x, 3x squared, 4x cubed, 5x to the fourth, 6x to the fifth, and so on and so forth. For the series 2n times x to the power of n, we can get 1 over 1 minus 2x as our generating function. Now this is far from unique. In fact, any series of the form c to the power of n, x to the power of n, will give a generating function of 1 over 1 minus cx. Taking the natural log of 1 over 1 minus x will then generate x to the power of n over n, starting at n equals 1. Examining its twin, e to the power of x, will generate 1 over n factorial times x to the power of n. Now this generating series in particular is important because we can use it to show that the derivative of e to the power of x is e to the power of x. Here, if we go term by term, we can take the derivative of 1 is 0, plus the derivative of x is 1, plus the derivative of x squared over 2 is x, plus the derivative of x to the power of 3 over 6 is x squared over 2, and so on and so forth. Confirming this, if we take the derivative of that power series, we get 1 plus x squared over 2 plus x to the power of 3 over 6, and so on and so forth, the same as before. Now to make the most use of these examples, we should look at how to find our own generating functions. In concrete mathematics, Knuth outlines steps to find a closed form of a generating function given a recurrence relation. First, you should write down a simple equation that expresses f sub n in terms of the elements of the sequence, and make sure that it's valid for all integers n. Then, you should multiply both sides of the equation by the auxiliary variable raised to the power of n, and then sum over all values of n. This should retrieve for us the infinite sum starting at n equals 0 of f sub n times x to the power of n on the left side of the equation, which is then our signature for the generating function. Finally, you should simplify the right side of the equation so you can find a closed form of big F of x. Now once you have this, you could expand it into a power series and read off the coefficients of x to the power of n as n grows without bounds to retrieve the original sequence. Now to show that this method works, we can use it to reinforce our generating function for the Fibonacci sequence. We'll start with the recurrence relation f sub n is equal to f sub n minus 1 plus f sub n minus 2, which can then be used to describe the Fibonacci sequence. Now, to make sure that this works with all integers, we have to add the Kronecker delta of n comma 0, just so that f sub 0 is equal to 1. Using x as our auxiliary variable, step 2 will retrieve for us f sub n times x to the power of n is equal to f sub n minus 1 plus f sub n minus 2 plus Kronecker delta of n comma 0 times x to the power of n. We can then sum over every value of n, giving us the sum of f sub n times x to the power of n is equal to the sum of f sub n minus 1 times x to the power of n plus the sum of f sub n minus 2 times x to the power of n plus 1. Simplifying this equation using the properties we've shown in the last couple of slides will retrieve us big F of x is equal to x times big F of x plus x squared times big F of x plus 1. From here, we can do the same shifting of variables as we did the last time, taking x times big F of x plus x squared times big F of x and subtracting that from both sides, and then dividing through by 1 minus x squared. Now we can finally put this to rest once and for all by giving the Wolfram language generating function of Fibonacci of n plus 1, comma n, comma x, in which it'll spit back negative 1 over negative 1 plus x squared, which is equivalent to our generating function. I should note here that I had to give the Fibonacci of n plus 1, as the Wolfram language is 0 indexed. Now you've made it to the end of this lesson. In this lesson, we covered ordinary generating functions and their convolutions, some notable properties and examples of generating functions, and some steps to finding a closed form of a generating function given a recurrence relation. In the next lesson, we'll dive deep into some finite summations. Again, I'm Alistair Forsyth, and thank you for watching. Bye-bye.